All right, let's get started. So today we're going to be talking about efficient transformers that can process very long input sequences. And yeah, this is of course relevant for any application that wants to do document modeling, like long document modeling, where you want some sort of prediction that you're making, whether this be classification on the document or generation of the next word, to be conditioned on a very long input sequence. So before we start, some stuff from last time. So the midterm obviously is over. I think at this point we have a submission from everyone, but I haven't verified that yet. So I'll let you know on Wednesday, but please don't discuss the contents, at least publicly, on Piazza until then. Yeah, hope everyone think they did okay. We'll see. We'll start grading in the next couple of weeks, and you'll get your grades back and can submit regrade requests and so on in the middle of the month. So you'll have one more homework assignment. It's almost finished. It'll be released probably early next week, and it'll be due at the end of the month. And then, of course, your only other major deliverable is your final report, which is due May something, the mid-May, whenever the last day of exams is. So hopefully for the next month or so, you can keep most of your effort for this class focused on the final project. Homework 2 is basically about fine-tuning models like BERT and also language models like GPT-2, understanding how to use them in different scenarios and how to improve their performance in a variety of different transfer setups. So it's not particularly complex from like you don't have to write down any equations or anything like that, but you do have to go through quite a bit of code blocks on a Colab notebook to finish it. But hopefully it's useful for your project as well. And you'll have a couple more quizzes, but of course those are fairly low effort. So I see someone asked, when can we expect homework 1 grades? Hopefully soon. I'm not exactly sure on the status of the graders, so I will check, and hopefully in the next couple of weeks. All right, any other logistics questions? Anyone? Okay, so we will go over the solutions of the midterm on Wednesday if everyone has completed it by then. All right, so let's get to the topic of today's lecture, which is mainly on speeding up the self-attention mechanism that is in transformer language models. So as we know, both the memory and time complexity of self-attention, which of course is the building block of the transformer model, this is quadratic in the sequence length. So someone explain why that is. That's right. So every token needs to attend over every other token, right, in the fully unmasked self-attention case. And so thus, as you increase the sequence size, you have this quadratic dependency on the sequence length. So this is one of the major limiting factors behind just blindly scaling these models up to longer and longer sequence lengths. Actually, as an aside, today, just like 2 hours ago, Google released a new enormous language model that is like almost half, or maybe more than 500 billion parameters. So it's like maybe 3 or 4 times the size of GPT-3. I'm not sure, I doubt they released the model parameters, but there's a paper and blog post that you can check out. It seems to be able to do some very cool things. My student was saying it can like explain jokes, like why they're funny. I'm sure it can't explain every possible joke, but it seems to be able to do some cool things that GPT-3 can't do. So if you're interested in the just brute force scaling of language models, you should check that out. But anyway, even that kind of model, right, they have to pick maximum sequence length, which is going to be shorter than most of your average documents to train on, because as you get longer and longer sequences, your self-attention starts dominating the computations, and it's just not scalable. So we had some timing experiments. This is from a few years ago. So as you can see, we're using a 2080 Ti GPU. Nowadays, there are many better GPUs than this, but you can still get a sense of the issue as you try and generate or understand longer context. So if your prefix length is 100 tokens, so the columns here are the prefix length, and you're asking the model to generate the next 100 tokens, on a single 2080 Ti GPU, it takes 2.3 seconds. And if you ask it to generate 300 tokens, it takes about 7.3 seconds. And you can see that if the context size, the prefix length is longer, 300 tokens, and you ask it to generate the next 300 tokens, this shoots up to about 10 seconds. So in this bottom right cell over here. So you can imagine if you were trying to serve this model, right? You were serving some task, you had an API or something where your users would put in fairly long documents and expect to get out some sort of fairly long output. So one example could be a long-form question answering model like you saw in your exam and like we discussed in class, right? Here you might have, a fairly long question statement and also a very long answer that's generated. So in industry, of course, it's highly important to have to lower these kinds of times so you can serve more of these queries in parallel. Perhaps you can also do training faster if some improvements are made here. So yeah, this is practically very important to get these times down and also to kind of expand the length of the input documents that a transformer can process. As such, there is a ton of work on designing newer and newer types of transformers that don't have this quadratic dependency in the input length. This is a diagram from a survey conducted in 2020. If you were to do the same survey now, there would be many, many more variants of models that have been proposed. There are also papers that show like people have developed all of these different variants of transformers, but in the end, the vanilla transformer is still superior to all of them in controlled conditions. And so it's not really clear if any of these is a particularly good approach. Certainly nowadays, people tend to still just use the standard transformer as we've discussed in class, and none of these competing approaches has really taken off. In terms of industry who are scaling these models, they tend to use primarily transformers, perhaps with a few sparse layers thrown in, but nothing fancy like any of these. On the research side, though, there's a lot of work, as you can see, on developing, hopefully better versions of transformers that scale better. So there's 5 broad categories of improving these transformers and making them more efficient. So there are recurrent mechanisms. So we talked about recurrent neural networks, right? And one approach you might conceive of is, well, what if we have a transformer that encodes like local blocks of tokens, and then we have a recurrent mechanism over blocks of tokens. So maybe you have a transformer that computes a single representation of a block of tokens. Then you have a recurrent neural network that operates over those representations. So the recurrent neural network is not actually operating over the tokens of the document itself, but over some sort of chunked representations. Perhaps this is an efficient way to incorporate more context into your model's predictions without making it super inefficient. So the Transformer XL was one of the first variants proposed that integrated recurrent neural networks and transformers. There's also the compressive transformer, which is also an instance of a memory-based augmentation of a transformer, where you have a transformer modeling the local tokens. So maybe the preceding X tokens are modeled by a transformer, and then you have some external memory that you've computed of the global faraway context that is used to condition your transformer's prediction of the next word. So a lot of these memory-based models are like that. One interesting and very simple case is fixed or even random patterns of attention. So one of your exam questions was an instance of this, where we had someone who came up with this kind of nonsensical pattern, but it was a pattern nevertheless that removed the dependence on the input sequence length of at least the time complexity of the self-attention, right? So we'll see some examples of these later on in the lecture. Oftentimes it's surprising that even completely random self-attention patterns can work just as well as learned ones, which kind of calls into question the intuition behind self-attention, if that is indeed the case. There's a bunch of low-rank approximations of the full n by n self-attention matrix that have been proposed, and also maybe a little more intelligent than the fixed hard-coded attention patterns is learnable patterns that are still sparse, so they don't involve computing the self-attention over the full input sequence document. So this is a quick overview. There have been many more variants, as I said, that have been proposed since this diagram was made. For example, just a few weeks ago, there was a paper called recurrent block transformers, which I think did a much better job than the transformer Excel at incorporating both of these different types of neural networks together. So yeah, it's like almost every other day there's a new one of these coming out on Archive. So let's take a step back and just go over the self-attention computations again, so it can serve as kind of a foundation to the rest of the lecture. We also already saw these slides when we were talking about it before, but remember, if you have some input sequence, you do these projection to query key and value for every single token in the input. Then for every single token, you take the query vector and compute the dot product with all of the key vectors, right? So this is where you get that quadratic dependence. Then you perform this value weighted average, and then you do all your other computations in the transformer block, and then stack these layers on top of each other. So as the simplest of these variants goes, let's explore some of these fixed and fixed attention patterns instead of the learned ones. So one work by my group was simply to explore what happens if you take a machine translation model, like a transformer trained on machine translation, and you forbid it from actually learning any self-attention. Instead, you kind of just hard code some attention patterns at every position of the network. These are not dependent on the input at that position. They might just depend on what position of the input that you're at. So for example, here, let's say we're computing the attention distribution for this word Strickland. So normally I would take the query vector for Strickland, and I would compute the dot product between all the key vectors. Then I would take the softmax, and that's how I would get my distribution. But what if I just simply made a distribution where it's centered around the word immediately to the right of this word? Immediately to the left of this word, awards. And other than that, there's no dependency on the input at all. It's simply position-based. So here you can see that the distribution is centered around the word awards, and it's just a simple Gaussian centered around this word. There's nothing involving the actual word Strickland here, so we don't need to have a query. We don't need to have key vectors either. All we need is some value vectors, so we can take the average of them using these simple weights as the scores. So you can imagine hard coding many different attention patterns that you think would be useful, right? So maybe this one is looking at the word to the left of the current word. Maybe it would be useful to have a distribution around the word to the right of this word. Or maybe it would be useful to have the distribution centered around this particular word. So remember that in these kinds of models, we have multiple heads, so we can just use a different, either a different standard deviation, a different center. We could have a head that always looks at the beginning of the sentence, or a head that always looks at the end of the sentence. We could have a head that always looks at nouns or always looks at verbs. Like anything we intuitively might think a transformer is already doing, maybe we could build these heads in and not actually learn them. And if we do this intelligently, what happens to the performance of our translation model? So this is just showing that it's very easy to design these heads, and you don't actually have to do any sort of learning at all. So your training and your inference is much faster. And for those of you familiar with convolutional neural networks, we haven't talked about them in class. This is essentially equivalent to a 1D convolution using a fixed kernel, not a learned kernel. So in a transformer, you have three different types of self-attention. So you have the encoder, the decoder, and then the decoder cross-attention as well. All of these can be hard-coded in this way, although the cross-attention is a little more complicated to do so. So why might you think that making these fixed patterns for the cross-attention could be a little trickier? Any ideas? Exactly. So in cross-attention in the machine translation case, we don't actually know, we can't make something like this is this head is going to look at the word immediately to the left of this word, because the sequence that we're looking at is different than the target sequence, right? So now we're looking at the source sequence, and we might need to run an aligner or something to figure out, okay, this word Strickland is aligned to this particular token in the source sequence. Now, given this alignment, maybe I'll have this distribution, but it's more complex than just doing it over the same sequence. So yeah. Are the parameters, so these parameters are all fixed. So this is like the simplest possible. Actually, you could do even simpler than this. You could set everything to 0 except 1. So you could just have a binary head, and each head will just look at a different value vector. This can be done too, and this is probably the simplest possible thing that you could do. But yeah, all of these are completely fixed. Yeah, so that's a good point. You could imagine learning the parameters of this distribution rather than learning the attention scores themselves, right? So you could try and learn the mean or standard deviation of the distribution. There have been papers that do exactly this. Yeah, this cuts down the computation as well. But of course, there's something you lose when you do things like this. Okay, let's see here. So the memory complexity is O of number of layers, heads, n squared. Yeah, but I like the sequence length dominates the computation. So does GPU parallelization help reduce this? I mean, I'm not sure what D here means, but certainly the GPU parallelization reduces some of the computation cost at training time, but it's still bounded by the input sequence length, so it doesn't change the worst case complexity. Okay, so let's see what happens when you do this. You replace the learned self-attention with the hard-coded version. So on 6 different machine translation data sets, so this is English to German, German to English, English to Romanian, and vice versa, and English to French down here. This is what happens if you have a normal transformer model with all of the heads learned. So this is like the vanilla transformer with no modifications. And these are the blue scores. So we talked about the blue score, right? It's this n-gram overlap-based evaluation metric for machine translation. So if you do the hard-coded self-attention, your blue score is actually not impacted basically at all on some of the data sets. Sometimes it even improves, which is interesting because that is basically telling you that your learned self-attention is not doing anything more intelligent than simply focusing on different words surrounding a particular word in your target sequence or source sequence. On a bigger data set like English to French, it does do a little bit worse, like almost 1 blue point worse. So this is somewhat significant, but still not that bad. When you do this, it gives you some memory savings, first of all. So you can use 27% more tokens per batch. So this is great. Basically, this means you can fit 27% more tokens into a batch without getting out of memory issues on your GPU. Whereas if you learn the self-attention, you can only use fewer tokens per batch because now you have to store all of those attention computations during both forward and back prop. At test time, you get a big boost in decoding speed with this model. Since you don't have to compute these query key dot products anymore, you get a 30% speed up over the baseline transformer. And keep in mind that machine translation is generally a sentence-to-sentence level task. So the inputs are not that large. You can imagine if the inputs were documents and you were generating documents, your savings would be a lot bigger here. You would get much bigger speed ups over the baseline transformer in terms of decoding speed. So one of the morals of this story, which you will see over and over again with some of these other variants of transformers and attention, is that we still don't really understand what is making these models work for various tasks. And if you're in a setting, perhaps you're in an industry job and someone asks you to speed up this model, you can consider some fairly drastic simplifications to your model, even if they seem like they would completely break the whole intuition behind that model, and make the model faster without incurring a big performance penalty. So since we've done this work, there have been many other things proposed that are also simple. So one interesting paper that came out, I think last year, called the Shortformer, I think, was they basically trained their model on shorter sequences, and then at test time, they have a way, I think, of modifying the position embeddings to allow for even longer sequences to be input into the model, and it seems to work very well even though the model was just trained on these very short sequences. So if you're interested in training time speed ups, that's potentially one way to go as well. Okay, so we're going to cover just briefly a couple of these models on this diagram. We'll spend the most time on the routing transformer because I think it's particularly interesting. The Longformer is one of these models that's using fixed patterns, but more intelligently than the one that I just showed you with the hard-coded attention. The Linformer is doing one of these low-rank approximations. And then finally, we'll, at the end of class, talk about a couple of data sets that people have built to try and more intelligently evaluate whether these models are actually using context that is very distant from the current token. Because it's hard to even think about how a model should make use of such information. Okay, but let's take a look at some more intelligent fixed patterns first. One that's very popular is called local attention. And so here, you make a very simplifying assumption that each token can only attend over the last k tokens. If we think about the model from the exam, I guess I shouldn't talk about the exam. Okay, let me not do that. Although I do think everyone has taken the exam, but I'll leave that for now. But in this particular figure here, the white tokens are masked and the blue tokens are unmasked, and the diagonal is, of course, the current token. So you can see that here, if k is equal to, say, 4, we're looking at only the previous 4 tokens. And here, you can get rid of the dependence between the self-attention complexity and the input sequence length in this fashion. However, the sequence length here, so in the first layer at least, your contextualization of the current position's representation only takes into account the previous K tokens and no other tokens. So if you have a very long document, you're losing a lot of information early on in the network. Although higher up in the network, you will start to increase your effective window size, like the number of tokens that you're attending over with this kind of attention. In the Longformer model, we talked about, they proposed some other attention patterns that are a little more complicated than this local attention. So in this model, it's more like BERT, so you can attend on both sides. This is a left to right language model where you can't attend over the future. Here, as you can see in figure A, you have the full unmasked self-attention, so every token is looking at every other token. You can imagine the sliding window attention B is the analog of local attention to the unmasked self-attention setting, where here you're looking at K tokens on both sides of this current position. C is a little interesting. So here we have a dilated window. So you're going to look at every other token or every K tokens. So in effect, this allows you to expand your window size, but you miss tokens within that window. So intuitively, if you just think about a single layer transformer with one dilated sliding window attention layer, it wouldn't make too much sense, right? It means basically you're reading every other word and when you're processing the current word. But it's hard to think about what happens when you stack these layers one on top of another. Then eventually your current representation will take into account all of those missing tokens, even though at the first layer they might not have looked at them. So it's a very strange way of processing a sequence, right? Definitely not something like a human would do, but it gives you a bigger effective window size. So finally, there's the global attention plus the sliding window attention. So sliding window attention you can think of as local attention, which is dependent only on the position of the input sequence that you're at. But it might always be useful to focus on, say, the beginning of the sequence or certain types of words in the sequence. So you can mix these two things, like the global attention, regardless of where you are, will always look at these first two tokens, or I don't know, whatever this token is, maybe it was an important name or something like that. But you also have the local attention. So the Longformer basically integrates a lot of these different types of patterns into the model. And it shows that it can scale to fairly long documents, I think like 4,000 tokens or something like that. The Linformer, as you can see, very creative with the names, everything will have a former in it. The Linformer is taking a different approach where you take the n by n attention matrix. The idea of the Linformer is that let's just not form this matrix at all. Instead, before we form this matrix, let's take our keys and let's take our values, which are of size n by d and n by k, n by d, where n is the sequence length and d is the dimensionality of the representation, the keys and values. And let's do a projection where, let's do a projection to n by k, where k is much less than the sequence length. I think I actually got this wrong. This should probably be d by, okay, well, let's take a look at this figure down here. That should explain what's happening. Yeah, I think it should have been this k by d. So anyway, you have this k by n projection matrix, and you multiply it by your key matrix. So the keys are n by d, where n is the sequence length. So this approach it basically requires you to know the maximum sequence length n ahead of time. So you do the projection over the sequence length dimension. That's what's interesting about this approach, where essentially you're reducing the dimensionality on the sequence dimension instead of the vector dimension. So when you do this, you get k by n times n by d. You're left with a k by d matrix. So this is what this should have said, where k is much less than n. And now you can do your attention in this reduced dimensionality space, which does not depend on the sequence length. And then you can project it back to the original sequence length to do the final computation. But the important thing here is that you're not actually doing the attention computation over any sort of matrix that depends on the sequence length. You first just project this thing down to a much smaller matrix, which does not depend on the sequence length, and then you do the computation. What's the time complexity and memory complexity for Longformer? This depends on which head you're talking about here, but as you can see with the sliding window attention, this only depends on the size of the sliding window, so it scales just with whatever the size of the window is. And the dilated sliding window is similar. It's just you might be using the same number of tokens, but there's some gaps in between. So neither of these are n squared, although I think they do include some heads that have the full self-attention. So overall, it's still bounded by that. But yeah. All right, so in the Linformer, despite doing this low-rank approximation of the attention matrix, there's not much effect on the language model's perplexity. So they're training a transformer language model. This is not surprising. There's many other papers that show that you can replace the transformer attention with random attention and you still get no real impact on the perplexity, provided that you have a deep enough transformer model. So again, all of this is just to say that we don't really know what the importance of the self-attention mechanism really is in determining the performance of these models, at least at some scale. They also show in this Linformer setting that you can apply this approximation to BERT type models as well without incurring too much performance loss. Sometimes you can even do better than the comparison to the full transformer model. So to give you some context, there have been many of these different variants proposed, and they all also vary in the maximum length of the input document. So GPT-2 from 2019 is a full self-attention transformer model, could take in 1,024 tokens of context. There were some variants proposed a couple years ago, Big Bird and the Longformer that we talked about, that bumped this up to about 4,000 tokens using some of these mixture of sparse attention and fixed pattern attention. The routing transformer takes in 8,000 or so tokens, and just this year there were some papers released showing that through the aid of external memory, you can bump this up to like 16,000 tokens. So people have been making progress at expanding the sequence length of these models, like the maximum sequence length through all of these approaches. But one question is, how do you actually measure if a language model is making use of those 8,000 or 16,000 tokens of context, right? It's nice that theoretically speaking, you can feed in these sequences that are this long to a language model and see how well it does on a language modeling benchmark in terms of perplexity, but how is it actually using those faraway tokens? So in order to answer some of these questions, we have a couple different language modeling benchmarks. The most common one is the Penn Treebank or Wikitext 103. These are like news articles or Wikipedia articles, but unfortunately they're not very long on average. So in Penn Treebank, the average article is only 355 tokens. In Wikitext, it's about 3.6K tokens. So these are not long documents by any means. So the paper associated with the compressive transformer, which is one of these memory-based variants, introduced this data set called PG19, which is just a collection of books from the website Project Gutenberg. It's a bunch of these books in the public domain. And the average book length here is 69,000 tokens. So now you have this very huge input that you can throw all of these models at and see if they're actually helping. So we'll talk for a bit about an analysis of some of these different types of models on this PG19 data set. And specifically, there is a variant of the sparse attention that is called routing attention that we will be discussing in the context of this data set. So we talked about full attention and local attention. This, now we're talking again about left to right language models, not BERT type full attention unmasked language models or models. In routing attention, the sparsity is dependent on the actual word that you're at, not the position. So in local attention and that hard-coded attention and the dilated attention and whatever, the attention pattern was the same regardless of what word is at that position. In routing attention, this is not the case. So in routing attention, what we do is we compute these query and key projections, and then we perform clustering on them, so using something like k-means clustering. And so what this results in is, you have, say, 50 different clusters where each cluster contains some of the tokens in the input sequence. So here, these green tokens all belong to the same cluster, the blue tokens are in the same cluster, the red tokens are in the same cluster, and so on. And the idea is that once you do this clustering, then you can compute self-attention where a single token will only attend to other tokens that are in the same cluster. So here you can see that now the self-attention actually depends on the cluster membership of the current token, right? Not just the position of the current token. So this is an idea to kind of get more sparsity into the attention computation. So we're not computing full attention here, but we're not just doing this local attention, which is ignorant of the actual content of the word. We're doing this clustering and then doing attention over the clusters. So as I said, we first assign tokens to different clusters, then we perform intra-cluster attention. This reduces the complexity still, but also lets you have some kind of token-dependent attention. K-mean algo trains at each iteration of transformer training. Yeah, so at every batch, you would have to run the k-means to get the cluster assignments and then do the self-attention computation. So yeah, it's not the most efficient algorithm. You have to do it during training itself as you update the projection matrices at each layer. Okay, so let's take a look at how this works. So given this input sequence, so this is just an embedding sequence, we do the multi-headed projection. So we have, these queries, keys, values for every head. Then we do a clustering for every one of these heads. And so we find out that, for the values of head 2 or something like that, we got this clustering assignment where these 3 tokens are in the same cluster, these 3 tokens are in the same cluster, and so on. They cluster both the queries and keys using the same centroid vectors. So you're not doing a separate clustering for queries and keys, you're learning the same clusters and using those for both queries and keys. That said, the assignment of query and key at the same position could be to different clusters because those are different projections. So once you do the clustering, then you do this operation called gather, which is in PyTorch or any deep learning library, which allows you to get all the vectors that are at particular indices of your sequence. And so you would want to do this gather, acquire all of the vectors that belong to the same cluster, and now you can easily do this kind of intra-cluster attention over the resulting sequences that you get. So you compute the self-attention, and now you see that we're not using the full sequence here. We're just using whatever belongs to the same cluster when we're computing the self-attention. Now, once we perform the self-attention, we use another operation called scatter, which we basically will just provide each of these resulting output vectors from the self-attention with an index to go to, so we can map it back to the original sequence. So we can get back this kind of sequence, except now all of these tokens, these red tokens, have attended over each other, and all of these green tokens have attended over each other. So that's the basic idea. And once we do that, we can do our projection with the feed forward layer, and we get an output sequence which we can then feed to the next layer and continue. So that's basically how this kind of thing works. And they do a comparison on the PG19 data set to see if their approach is actually getting a lower perplexity than the competing methods. So the local transformer, right, which is just taking the last, I think this is the last 512 tokens, and it's considering that for the self-attention and dropping everything else from the self-attention. Then you have some other models. The Transformer XL is the one that combines recurrent models with transformers. The compressive transformer also uses a recurrent type of network combined with a transformer. And finally, we have the routing transformer. So you can see that it obtains a much lower perplexity than the local transformer on the PG19 data set. This is the one with those very long books. And so they use this result to show that this kind of routing attention is superior to methods that are agnostic of the current token's identity, like local attention, or methods that are using some sort of compressed memory instead of just a purely sparse self-attention mechanism like these two ones. So this kind of result, yeah, go ahead. Oh, do they constrain the size of the clusters? Yes, they do. So I forget exactly what kind of constraint they put, but I believe the clusters are made to be roughly equal size, if not identical size. I think they use some sort of hack to do this, though. Yeah. So the question is, what is the motivation behind doing this clustering thing? Yeah, so the motivation, the larger motivation behind any of these approaches is to reduce the number of items that are included in the self-attention computation, because we know that as we increase that sequence length, we get this quadratic hit from the complexity, right? So the question here is, why use something like this clustering attention over something simple like a fixed pattern that will allow you to attend over a fixed number of tokens? The intuition provided here is that you might want to attend over tokens that are somewhat similar to the current token, maybe in terms of part of speech or in terms of some other semantic or syntactic property that we don't actually know about. And maybe because this is happening at every layer and every head, each head can decide a different notion of similarity that can be used to guide this clustering to focus on different properties. So the idea is that instead of having just a fixed block of tokens that you're always attending over, regardless of the identity of the word at that position, you're now doing something potentially more intelligent, or at least you're allowing the model to learn which tokens it should attend over if it has this kind of sparse constraint. In time complexity? So they didn't actually measure the, yeah, theoretically, yes, but practically speaking, you have to show this with like wall clock time experiments and maybe like decoding and so on. But practically speaking, you incur a penalty for doing this k-means computation which I think it makes it very slow to decode from the model in practice. Perhaps at like a very long sequence length, this is not a factor, but at least currently it's a huge factor. So it's very slow to decode from this model at test time, even though it does not have a quadratic dependency in the sequence length. Yeah, so that's another thing that you'll see in a lot of these papers is that they introduce some fancy mechanism that reduces the complexity, but actually makes it slower for all practical setups of the model. Yeah. Yeah, but you can do that using the fast nearest neighbor type algorithms, which is what they do here. Yeah, so we talked about those with the retrieval augmented models as well. Those need to be used here, otherwise it's just infeasible. Yeah. Okay, so the first question was how do they select how many clusters there are? This is just a hyperparameter, so the only answer is they try a bunch and find the one that has the lowest perplexity. The second question is more interesting. Why do they do intra-cluster attention versus inter-cluster attention? Because you might imagine that actually diversity of the self-attention is more important than looking at tokens that are similar in some property. Like if you imagine you're looking at a semantic similarity, so your clusters are based on meaning related similarity, then maybe it would be useful to look at things that don't mean the same thing, right? This is a great question. I'm not really sure why. You could certainly try some other sorts of attention mechanisms that are dependent on the clusters but are more maybe complex in the intra-cluster assignment. Maybe you could attend over one or some tokens from each cluster instead or something like that. Yeah, I don't have a good answer. I think that is a very valid question though. It's hard to tell what the model is actually doing. Again, with this paper, they did not analyze what kinds of tokens are getting grouped together in this clustering assignment, so it's very hard to tell. To be fair to them, it's happening at every layer and every head, so there's a lot of different things to analyze, but yeah, it's a good question. Okay, so yeah, I mean, kind of relatedly, one thing that we might wonder is, so how are these models exactly computing representations of these huge contexts? And you can think about like, what would a human do if, let's say, imagine you're reading a book, right? And your goal is to read this whole book and then write the next paragraph of the book. Maybe the book is unfinished. So how would you do this? Like, you probably wouldn't do something like dilated attention where you read every other word of the book and then read the words you missed in the second read through and then do something, right? That doesn't make sense. You probably would read the book left to right, and it's not like you actually remember the words that you have read like 50 pages ago to the exact order and identity, right? That is certainly not what you're doing, unless you're some kind of like perfect memory person. But most of you, I imagine, are not. And so what do you think we're doing? We're probably forming some sorts of higher level abstract representations of what is happening in that book in our brain, right? We probably know, roughly what each character's personality is and what the major events are and where they've been moving and what has happened to them. But we couldn't tell you exactly the words that occurred, X tokens ago. But all of these transformer models, in theory, could, right? They have access at every layer to every single word and the position of every single word. And they don't actually have to do this kind of compression of the context into some structured or more abstract representation that is useful for them to generate the next paragraph. So it's very unclear if the way that we've just described with all of these approaches is the correct way to scale these models. If we're taking inspiration from human language processing, then perhaps we should not show the language model such huge input sequences, but we should allow it to do some compression first before actually doing the self-attention. So one of the papers from my student Simang and Kalpesh was more along the line of, let's say we have all these existing long-range transformers, how are they actually making use of the long-term context? Or just because they're theoretically able to model 8,000 tokens of input, in practice, how do they do if we chop off some of the document? Or what happens if we perturb the document that's very far away? What if we shuffle the words or replace the words with some random other article? How does the performance get affected? And to summarize, it seems like they are not sensitive to anything outside the last 1,000 or 2,000 words, which maybe makes sense. If you imagine your task is given some document, you're going to predict the next word. How often do you think it is that you actually need to encode some information from 5,000 words ago? Probably in many cases you can get away with just the current sentence or maybe the last 3 sentences or the last paragraph, right? It would have to be quite a complex context to require you to search back multiple chapters in the past to make the correct prediction of the next word. So what really is the effect of the longer context? One thing we did was look at the PG19, so this is this long book data set, the validation set, and we wanted to compare this routing transformer model, this one here, which obtains this perplexity of 33, against this worse model, the local transformer, which obtains the perplexity of 39. And so the claim made in this paper is that the routing transformer is doing a superior job at modeling the faraway tokens, and that's why you see this perplexity decrease. But it turns out that the gap in perplexity between these two models is roughly the same regardless of the size of the input document. So sure, there's this 6-point perplexity improvement when you consider 8,000 something tokens. This is the last endpoint of this plot. Basically, the blue one here is the perplexity of the routing transformer. The green is the perplexity of the local transformer. The claim that the routing attention is superior to the local attention because the routing attention is more intelligently modeling the global context would be borne out if we saw this gap increasing as the sequence length also increased. But you can see it's flat, basically, even when you get a couple hundred tokens of context as input, the routing attention is superior to the local attention. So what does this mean? This suggests that the routing attention might just be a better overall self-attention mechanism than local attention. It has nothing to do with better modeling of faraway context. So this is not particularly interesting to us if we're focused on models that actually learn intelligent representations of the global context. So we did some further experiments that basically found that regardless of the genre, or regardless of if this was a single narrative or something like a journal or a textbook where the chapters are not, they could be about different things, we see the same kind of trends that as you add more and more context, your perplexity is not really dropping all that much. And finally, and perhaps most sadly for these models at least, we did a couple experiments where we took this 8,000 token long input sequence and we perturbed the first n tokens of the sequence. So these are the ones that are farthest away from the target token. And these perturbations could be shuffling the words in this context to destroy the word order information. It could be replace the perturbed prefix with a completely random sequence from a different document, which has no relationship to the current target document. And it could also be dropping out specific types of tokens. The end of the day, these plots show that basically until the perturbation starts affecting the tokens that are within the last 2,000 tokens. So here, basically, if you extend this perturb prefix to the first 6,000 tokens even of the sequence, it makes no impact on the perplexity, which suggests that these models are basically completely insensitive to tokens that are far away in their context. So overall, it suggests that while theoretically the model can handle sequences of 8,000 tokens, in practice, these tokens make no contribution towards the prediction of the next word. And another thing it suggests is that we should think more carefully about this training objective itself. So GPT-3 and this new Google model and all of these huge models are trained specifically to predict the next word given some input context. But like we can't really even think of situations in which you need some huge context to be able to predict a single token into the future. Maybe it makes more sense to predict, like a full sequence into the future, but a single token usually is dominated on very local dependencies between the tokens that are most nearby to that token. So even if you imagine that, say, 99% of next word predictions, you only need the last 500 tokens to make them properly. And maybe there's a few tokens that require the long-range context. These models are not going to learn that, even regardless of how large they are, right? If most of their training data involves just looking in a local neighborhood to determine the identity of the next word, they're probably not going to need to develop an intelligent model of the long-range context like we would do when we're reading through something that's this long. So that's kind of looking forward to the future. Instead of just scaling up these next word prediction type language models, perhaps people should think about different training objectives that involve more global kinds of language understanding rather than just local language understanding. So maybe something you can think about. Yeah. Yeah, so text summarization, the question is, in a task like text summarization, don't you need the global context because the summary that you produce needs to summarize an entire article? That's true, but text summarization also has some simplifying properties that perhaps make it less necessary for a model to actually understand the full context. So a lot of summarization is copying, right? So if you see an important fact or sentence, you might just want to copy it into your summary. In fact, in text summarization, a major branch of text summarization is called extractive summarization, in which the summary that you produce is just a sample of some sentences that occur in the document. So you're not even generating any text, you're just selecting which sentences are most important and combining them together to form a summary. In abstractive summarization, you have a model that's actually generating token by token the words of the summary in your, what you said might be more relevant, but still this model is going to learn essentially to copy and maybe rephrase or better combine sentences from the original document. So I don't think any summarization system to this point has actually required the understanding of the full kind of structure of that document. I think summarization basically boils down to select the important sentences and perhaps rephrase them in some way. But yeah, we will talk at the end of this lecture about some perhaps more complex tasks that involve long-range understanding. Any other questions or comments? All right. And finally, one interesting finding is we can do these kinds of experiments that are like the perturbation, except we can put a kind of sequence, like we call it a canary sequence. Basically, you have some sequence that you want the model to, you want to see whether the model can copy this sequence from its context. So kind of relevant to what we were just talking about. So maybe we have a sequence like, you know, from that practice exam problem, Harry Potter's social security number is XYZ. One thing we can do is we can have an 8,000 token long sequence, and we can place this target sequence at different positions of this sequence. And so how well does the model do at predicting the duplicated sequence depending on how far away the target token is from the first occurrence of this sequence? So you can see that for both the routing transformer and the local transformer, the perplexity of this target sequence kind of flattens out about 1,500 tokens in and does not improve after that. So this suggests that after the target sequence gets sufficiently far away from the current words that we're predicting, the model is just unable to remember that it existed, and it's unable to, you know, copy it from its global context. So essentially the word order in the long-range context and also the identity of the words is not really encoded well by any of these models. And so that is also the case with humans, right? We don't really encode the order of specific words or sentences in very, very distant context. We basically have our own kind of summary. Who knows how it's stored in our brains, but it's certainly not stored like these models are storing them. Okay, so finally I wanted to talk about two different data sets that are kind of, they've been created to better evaluate and support the development of these long-range transformer models, because it's very clear that we would like to have models that are able to understand long documents, right? That makes sense for many different applications of NLP. And currently, the best way, so for practical purposes, if you're ever faced with a task where you have a huge document as input, the best thing to do is just to chunk it up into smaller segments and put each segment into BERT or something, and somehow aggregate those vectors through, say, pooling or something like that to represent your full document. So in this method, completely breaks the dependencies between those chunks, but it's still the best that you can do with the modern models that we have. But this approach is so obviously limited that people want to devise better and better models that can take in and understand longer and longer documents. One data set that recently came out, I think in December, is called Quality. So it's a question answering data set where the questions are about a fairly long story, and they require understanding information from many different parts of the story. So you can see in this example, the story is about 6,400 tokens. It takes a human about 30 minutes to read through this whole story. And they have a crowdsourcing workflow where Mechanical Turk workers, or I think they got workers from Upwork, which is another crowdsourcing site, will read through the story and then write these questions. So this question is, which is the best representation of Dr. Lessing's worries about his book? So this is a question that is not like a squad-like question, right? It actually requires you to navigate to the part of the story that is talking about Dr. Lessing's book, which could be scattered throughout the entire story, and then identify what the nature of his worries are. This is a multiple choice data set, so the correct answer is he's concerned about having to back up his claims, could keep him from being objective, but the incorrect answers are written in such a way to also be plausible. So he is anxious about the amount of time it will take to revise or he's having second thoughts about his qualifications to publish a volume like this. All right. And so to correctly answer this question, it requires actually reading and understanding the story. And to make sure that this is actually the case, they get other crowd workers to answer these questions and give them varying amounts of the story with which to answer the questions. So if they could only answer the question in like one sentence from the story, then it's not good for this data set, so they don't include it. Here you can say that, all of these workers thought that this this question could be answered with 1 or 2 paragraphs from the story, although this worker has said that maybe you need to read most of the story in order to answer this question. Yeah, this is one interesting data set that currently human performance is well beyond any of these models, but people can start developing their models on this data set to further improve the long context understanding. Second and last, I wanted to talk about a data set that my student Simong, who did this perturbation experiment, has recently developed called Chapter Break. And this is a data set that's specifically related to long books that have multiple chapters. And the idea is basically that at a chapter boundary in, say, a novel, you have a lot of uncertainty in terms of the time and location and point of view and character and focus of the next chapter. Like at the beginning of a new chapter, a lot of things could change, right? You could shift the location, you could move a few years ahead in time, you could shift the point of view to a different character, and it really requires a lot of long-range understanding of the context in order to make sense of these transitions, like which of these. So basically here, this yellow box is a snippet of the book Slaughterhouse-Five by Kurt Vonnegut. This is like a classic book that involves time travel and aliens and World War II and so on. And it's a very, very complicated story to follow. So this character, Billy Pilgrim, at the beginning, he becomes unstuck in time. So he starts like wandering, he starts traveling back and forth between these different events. So first, he is in 1944. Then after 6,000 words of the story, you see that the date has shifted to 1967, and now he's 44 years old. Then after 3,000 more words, the story shifts to World War II. He's like a soldier there, and then he travels to 1967, and he gets kidnapped by some aliens from this planet Tralfamador. And so then, this is the end of, say, chapter 3. This task then gives a model 3 different candidates for what is the real start of the next chapter, chapter 4. So the correct answer is Billy Pilgrim could not sleep on his daughter's wedding night. He was 44. And the way a model can figure this out is in the previous chapter, it says he traveled to 1967. And you know that way back in the context, in 1967, he was 44 years old. So if it says that he's 44, that's kind of a sign that this candidate has the right context. But you can see that the incorrect context, so these red boxes here, these mention entities like Tralfamador and Billy Pilgrim that are in this context and that could be plausible beginnings of the next chapter. So it really requires a model to have a full understanding of this narrative and all the different shifts in the point of view and location and so on to correctly disambiguate the correct start of the next chapter from all the incorrect answers. So this is a very hard task. The routing transformer and all of these other models perform terribly at it, which is not surprising because they are not actually sensitive to anything that happens in the long-term context. And yeah, hopefully with data sets like these, next time I teach this class, I can be more optimistic about some of these models. But yeah, okay, so any final questions? Yeah. Yeah, that's right. So here, in all of these cases, we take a pre-trained language model that has been trained on something like PG19, so these very long books, and we evaluate it on this data set. But you could certainly imagine training on a data set like this. However, there are not that many examples because it's hard to find things with chapters in them. This data set also contains a huge amount of fan fiction narratives, which are divided into chapters, and a lot of them are about Harry Potter or Twilight, so not much in terms of topical diversity, but yeah, there's a lot of different types of transitions in the data set, but still definitely not something you would train on. It's more of both of these. I mean, this one you could actually train on too, although it's kind of small in itself. I think both of these data sets are much more useful as evaluation for a pre-trained language model. Did you have a question?
Yeah, I was thinking like the reason why we developed transformers was because RNNs were not able to encode information from cars.
Mm-hmm.
And we are seeing the same thing with transformers, they're not able to encode it. So what like do we need to look for a new method, or is it the task that
Yeah, so that's a great question. Basically, the question is, when we were talking about RNNs, we talked about all these issues like the vanishing gradient and so on, which limits their ability to actually leverage the long-term context. And then we talked about transformers as a way maybe, or attention itself as a way of getting around some of these obstacles. But now we're saying that they still are not taking advantage of the long-term context. One thing I would say to that is the effective context window size, even though it's limited, as I've shown here, has certainly increased dramatically from a few years ago, where language models beyond the last 20 words, probably you wouldn't get any benefit. But now, it's impressive still that in a curve like this, you can see that having 2,000 tokens of context is clearly better than having 1,000 tokens. That's something that you would never see even like 3 or 4 years ago. So I think our ambitions are big, but there is some tangible progress being made in terms of like local language modeling. That said, your second question is very relevant. Like, do you think the field should focus on new models that potentially have a better ability to handle this global context modeling? Or should we focus on new tasks? Personally, I think focusing on new tasks is more interesting. So we've been doing next word prediction for so long now. Perhaps we should stop just brute force scaling them and think more carefully about whether there are actually other objectives that could lead to more intelligent behavior from these models rather than just predicting the next word. Because like one thing we did in my lab for one of our lab meetings was we set up this, we basically tried to do human language modeling. So we'd have everyone read some context and then predict what word comes next. And I think basically 100% of the time no one was reading past like the previous 2 or 3 sentences to make a reasonable guess. So yeah, I think that training objective needs more thought, and not as many people are thinking about that compared to the different architectures, because it's always fun to make up a new model, but it's harder to validate the effectiveness of a new training objective. I mean, there are requirements of the training objective, right? It should ideally be self-supervised, so we can just create it from arbitrary text and not require labels. And yeah, it should require some more intelligent handling of the long discourse context that we see in a document. So yeah, I don't know, maybe we'll see something in the next year or two. Okay, so see everyone next time.